So this paper is about the evaluation of damages, inductive damages on living materials by a method called reverberation chamber. One common concern is the evaluation of the internal material damages is the appropriate method. The reverberation chamber is the method used for the analysis, and it is based on the electromagnetic waves in the range of this paper from 500 megahertz to 6 gigahertz. And we analyzed the absorption cross-section, ACS, of different material samples made of different kinds of concrete. And the analysis focused on the difference between intact and damaged sample. The average absorption, that is the capacity of the material of absorb the electromagnetic wave, is of fundamental importance to predict the statistical field behavior, showing fluctuation and fading in indoor and outdoor electromagnetic environments. Permittivity and permeability are intrinsic properties of the materials, but absorption properties depend on geometry and wave polarization and direction of incidence of the waves. So we have a lot of variables in this phenomenon, and the complete characterization of the absorption properties requires the repetition of the measurement using several angles of incident and polarization. It is made by the use of mechanical procedures that include the statistical optimization of the electromagnetic field distribution in the reverberation channel. So they are made in such a way that the electromagnetic field is statistically uniform and isotropic. In this paper, the ACS of the materials is evaluated, and the steps are evaluation of the quality factor and of the empty chamber, so without samples inside, and the loaded chamber with sample in. The frequency range is this one. So we analyzed three kinds of concrete. The first one we call white concrete, and it is a cellular mixture of concretes and quartz sand. It is lightweight, waterproof, and fireproof. So we analyzed bricks of laterite, vibration pressed concrete based on expanded clay, with some not specified additions, and bricks of sample concrete that is called CLS. And for the samples, the inductive damages are cracks deployed in the whole length of bricks, large 4.5 centimeters and 5 centimeters for the large damage sample, large 2.5 centimeters before for simple damage samples. Here some pictures, laterite on the left, simple and intact and with cracks, white concrete, with cracks, and CLS. The chamber is of cylindrical shape. It is very large. This table is 50, not 5, and the resonant frequency of the fundamental module is 50 megahertz, and the lower usable frequency is about 250 megahertz. Polystyrene foam support that we use for as a sample. The stirrer is vertical, Z-folded, made in aluminum, and it is 2 meters high and 1.4 meters wide. 360 stirrer in one position have been considered, so we had 1 degree step. Two transmitting LCD horn antennas are used in the the facility is completed by a VNA, vector network analyzer, that is an AGIX, that is used for measure the transmission coefficient between the containers, so S1, 1, 2, S2, 1. And of course also S1, 1, S2. The IF bandwidth is 1 kHz, and 5 seconds sweep time was chosen for the measure. These are some pictures of the chamber, and this chamber was used once as a space simulator for some macro satellites. Now we are using it as a reverberation chamber. We had to cover these holes with aluminum foils. And here you can see how we arrange the chamber. We have 2 antennas, the steerer, and the cylinder. The ACS determination is quite a complex process. So, all the electromagnetic quantities have to be ensemble average of the steerer rotation. So the ACS is defined as PS or SE, where PS is the power dissipated by the sample, and SI is the incident scalar power density. We consider ensemble average over the steerer rotation and frequency steering. So we have 360 measures, and we average every measure. So we obtain statistical uniformity of the total field magnitude. Of course, spectral characteristics of a multi-steerer cavity are sensible to energy perturbations. So we have to calculate total losses by multiple penetration. Wall losses, antenna losses, and material sample losses. So we have to calculate the Q factor. That is the probability that the material has to absorb electromagnetic radiation. It is only number without any and this is the formula, and QS is the sample, and QU is the factor measured without the material sample. Q with the sample inside the chamber, and the contribution QS is the sample dissipation, that is the difference between the products. After we can go on to the ACS, that is calculated as a function of QS with the volume of the chamber and the lambda, that is the wavelength of the reverberation frequency at the moment of the measure. So it is for every measure we have a lambda, and we have to repeat the measure for every step. And this is the formula for Q. We performed this measure, and we have on the left the latte, and on the right the white concrete. And we have two main differences in the frequency behavior. The blue line for both the plots is the large damage. The green line is the damaged material, and the red one is the intact material. For laterite, the ACS reduces with the frequency, while for white concrete, the ACS increases with the frequency, and this is probably due to different morphology and chemical composition of materials. For laterite, we can assume that if the electric conductivity increases, the ACS reduces, since the electromagnetic fluids are really reflected by the surface. And it is often observed in materials made of composites where metallic micro and nanoparticles are dispersed in high wave concentration. For the white concrete, on the contrary, if the porosity and the electric conductivity allow the electromagnetic wave to propagate, so the electromagnetic wave are easily absorbed and converted in energy losses. In this scenario, the ACS increases. We observed also a frequency threshold above which the ACS difference between materials and their corresponding reverberation became observable. And this is important because if we want to perform some other measures with higher frequencies, we have to consider which wavelength consider. And the higher is the frequency, the greater the probability that the electromagnetic wave propagates in the fractures. And we observed then that below about 2 GHz, there are apparently no difference in the ACS of materials in this frequency range. Of course, if we consider, as an example, 20 GHz or higher, maybe we can observe a difference, a higher difference. So, due to the higher reflectivity of the white concrete, the maximum ACS variation is relatively higher than white concrete material. And for large damaged sample, laterite presents an increasing of the ACS at frequency higher than 3.8 GHz. This is the measure for CLS, and in this case, we observed only a small difference between the broken and unbroken material, and it is visible in the frequency range 2.4 GHz here. In conclusion, we focus on the microwave absorption cross-section of several concrete bricks in the frequency range 500 MHz, 6 GHz. We considered laterite, where the ACS reduces with the frequency, and white concrete, where the ACS increases with the frequency. For both categories, below 2 GHz, there are apparently no difference in the ACS of materials. For CLS, we observed differences only in the frequency range 2.4 to GHz. Further studies will focus on the attention on the electrochemical properties of this material in order to have a complete overview of the characteristics. Thank you.